What's our status? We're done with part one. Part one was about how to make decisions, and it was all about search and planning in different kinds of environments. Now we're going to switch gears to probabilistic reasoning. What are some applications of probabilistic reasoning? Well, we've already seen in search and planning that often probabilities come up, and we've assumed these probabilities are given to us. In reality, that's not necessarily the case. Often you'll have to compute those probabilities from other probabilities that are given to you, or maybe from having empirical observations and building a model from that. So we'll be able to compute the probabilities that come up in our planning and search. There are also other applications of probabilistic reasoning that are just probabilistic reasoning in and of its own. For example, diagnosis. You measure a couple of things on a patient, maybe take temperature, some measurements of chemicals in the blood. That none of these directly tell you what disease the patient might have, but it'll allow you to update your distribution over what the likely diseases might be because you have some model for how diseases cause symptoms. And with probabilistic reasoning, you'll be able to, in some sense, reverse that model to go back from measuring the symptoms to inferring what the likely diseases are that are causing it. Speech recognition. You typically have a good model for if a certain word were to be said, here are common pronunciations of that word. That's the model you start from. Then the data you get is pronunciations. And somehow you got to recover out of that what words were being said. So again, the same type of reasoning where you start with a model that works in one direction, and probabilistic reasoning will allow you to reason in the opposite direction. Tracking objects, similarly there. Let's say you're trying to track a rocket that you're sending to the moon. You want to know where it is and based on that decide how much to boost each side of the rocket. Well, what would you run? Well, you would run probabilistic inference. Your measurements would be inertial measurements, maybe based on cameras. You'd see where certain objects are in the sky, and that'll help you know where your rocket is right now. You have models for if you were in a certain location, what you would measure, and you're going to invert those models in probabilistic reasoning from the measurements go to what the likely states are. Robot mapping, we'll see more of that later. Genetics, you can imagine, let's say there's a gene that could lead to a certain disease later in life, and now maybe you want to figure out, given somebody had that disease later in life, was the probability of them having that particular gene? And then maybe from there infer, well, was the likelihood of their brother going to have the same disease and so forth? That's all probabilistic reasoning, reasoning about variables that you don't get to observe directly through probabilistic models. Error correcting codes. Let's say you send something over a noisy channel, and if you send a 0, sometimes it comes out as a 1, sometimes it comes out as a 0. Then just sending the 0 not going to help you, right? People won't know what you send. One solution is to say, I'm going to send 3 repeats of everything. So I send 0, 0, 0, and that means just 1, 0. And then if sometimes things get flipped, I can still on the other side look at what the majority count is, and if there's 2 zeros, well then likely it was a 3 zeros sent originally. And you can do inference and compute the probability that indeed 3 zeros were sent initially. There are more complicated ways of doing this, but again, this is an example of probabilistic inference. You have a model for how your channel tends to flip bits, and then based on that model, and based on a prior distribution of what you think people are likely sending, either triples of zeros or triples of ones, you can then infer what they might have sent based on what you get to measure. There are many more examples. In some sense, this is where, when we in the very first lecture were talking about the old AI, what people were doing back in the 50s and the 60s, those are the things we already studied. Not everything they did then, but those are the kind of topics that they studied then are the ones we already covered. These new topics now are the ones that came about in the 90s when we had the new AI sprint coming around and people started to come up with probabilistic tools to deal with uncertainty. They realized it's needed to somehow handle uncertainty more robustly than with logical statements, and probability ended up being the method of choice and still is the method of choice. In the very last part of this course, the last 3-4 weeks, we'll look at machine learning. There we'll actually, rather than starting from a distribution and convert it into a distribution that we care about, we'll start from data and turn that into a distribution. Okay, probability. One high-level statement here is also that at this point, we shift gears not only from, in some sense, the old AI to the new AI, but we also shift gears from very computer science-y AI to very mathematical AI. So we're going to do a lot of math and equations, and it's going to be like that for a long time. So if any equations on the slides look like, oh, I have to think at least 5 seconds to understand what that equation means, that's probably meaning you're going to be in trouble later in the course. So all the kind of things we see today in lecture, you want to just be able to see that slide and be like, oh yeah, I know that. I can't believe we're even looking at this. That's when you're in good shape. So you might want to review this lecture at some point. So what are we going to cover? Today we're actually going to cover, in some sense, everything we're going to cover in the next 4 weeks. Every concept we're going to see in the next 4 weeks we're going to see today. But what we're not going to do yet is worry about computational complexity. So people knew about probability a long time ago, and it turns out to efficiently compute with probability distributions over large numbers of variables is very tricky. That's what we're going to be busy with the next few weeks, figuring out how to do that. But conceptually, pure mathematically, the types of expressions that we're going to be working with and the types of inference we're going to do is the same as what we're going to see today. The big difference between today and the next 4 weeks is today we don't worry about computational cycles. In the next 4 weeks we will. And we'll make things efficient. So we'll look at random variables, joint and marginal distributions and conditional distributions, the product rule, chain rule, Bayes rule, how to do inference with those, and then we'll look at a concept of independence, and we'll extend that next time to conditional independence, and then we'll be off to computational complexity things. Not in terms of big O computations, but just new algorithms to do things fast with lots of random variables. Okay. Just keep that in mind. Let's look at an example first. A little motivating example. So what are we looking at here? We have a ghost in a grid. The twist is that we're not going to know where the ghost is. But we have a sensor. We can put that sensor on a grid square, and then it'll give us a color back. Green, yellow, orange, or red. How does the sensor work? The sensor works based on how far away the ghost is from that particular square. So the sensor model looks something like this. And this is just for one distance. This is for the distance of the ghost being 3 steps away from your sensor. There's a model for the ghost being 0 steps away, 1, 2, 3, 4, 5, and so forth. So there's many of these models. Together they form the sensor model. If the ghost were to be 3 steps away, then this is the sensor model. Probability of measuring red is 5%, orange 15%, yellow 50%, and green 30%. So you can think of this as, well, the sensor was kind of built to measure yellow when the ghost is 3 steps away, but it's not super accurate and sometimes measures something else. We need a lot more tables to completely specify the sensor, but you can imagine something similar where red is typical for 0 steps away, orange for 1 or 2, yellow for 3 or 4, and 5 or more. The typical measurement is green, with some noise in what you actually get. Then let's take a look at that system in action. Here's our game. New game. Right now, we're not afraid of the ghosts anymore. We're going to kill the ghosts. We have a gun, and we're going to get them. Unfortunately, we don't know where the ghost is. It's just all blue squares. We have no idea. We have a sensor, though. So we're going to check out, well, let's measure here. When I click, I get a measurement green. That means the ghost is likely pretty far away. So let's measure far away from here. How about here? Orange, that's a good sign. How about here? Yellow, not as good. Yellow, no. Orange, orange. Red, that's a really good sign. But it doesn't mean the ghost is guaranteed to be there on the red square. Because it's a noisy sensor. Sometimes it will measure red when the ghost is actually not there. Let's see, orange and orange. But now we've gotten a lot of evidence that the ghost is likely in this square down here. Because there's orange measured around it and then red on it. So let's bust the ghost. At least hope that we will. We'll pick that red square here. See what happens. Hit. We got it. All right. So now let's play this game again, but in a slightly different way. Let's play it in a way that we're going to be thinking about it. For the computer, what will be going on here? For the computer, there's a probability distribution. And initially, it's 2% everywhere, the uniform distribution, equally likely that the ghost is in every possible square. Then, after we measure, The ghost doesn't have to be in the same spot, but we can always check it just in case. After we measure, we see that these numbers change. We haven't yet told you how we compute the change of numbers. But you can imagine that the distribution changes because you have a sensory measurement. And we now say, well, maybe out here, that's not great. But even with just those two measurements, we now have it narrowed down to kind of this circle here around the yellow one as pretty likely. Maybe let's try it down here. Not good. Now there's a lot of probability that's over here and in that region here. Let's try here. Even though we haven't been close to that red colored square there, we have a very high probability already there. So likely the ghost is there. Let's go measure and see what's going on. Oh, maybe the ghost is not there. We measured green. Let's try nearby because maybe it was just a noisy measurement and we got unlucky. Orange, orange, yellow, green, yellow. So, well, maybe the ghost is not around here. Now it's pretty likely over here. Let's check. Oh, 0.97. That's pretty likely. Let's go for it. We got it. All right. So that's the probabilistic reasoning. Underneath is the updating of these numbers. That's what we're going to be looking at for the next 4 weeks. After that, we'll start thinking about, now we know how to do the probabilistic reasoning. How do you decide where to go measure? What are the most informative measurements? And then how do you decide whether to still measure or maybe already hit? That's for after we've done with probabilistic reasoning, but that's an important component too that we'll get to. And when your project 4 comes out, you'll get to chase the ghosts because they will actually even be moving around. That was it. Here we go. So that's Ghostbusters. All right. So how about uncertainty? What kind of uncertainty is there? What are the variables we're thinking about? There are observed variables. That's the evidence. Those are the variables you know the value of. After we did a sensory measurement in a particular square, we know the value of the sensory measurement for that square. The unobserved variables are, well, squares where you haven't measured yet. What the sensory measurement outcome would be is unobserved. And then there is the unobserved variable you really care about is the position of the ghost. So there typically are 2 types of unobserved variables. The ones you want to find out something about and ones that are just present but you might not really use potentially. Then we have a model. The model, in this case a probability distribution model, that tells us something about the relationship between where a ghost is and what would be measured depending on where the ghost is. All right. So what are the random variables? They're just variables that can take on values and we'll have a distribution over them. So one example is it raining or not? Is it hot or cold? How long will it take to drive to work? Location coordinates. Where is the ghost? Note that we denote all of these random variables with capitals. That's notation. That's a choice. It's a very common choice, though, not just for this class. Pretty much everywhere with probability. The random variables are capitalized. Then they have domains. Just like for CSPs, the variables have domains. We have domains here too. R, raining or not, could be true or false. And then another piece of notation that we'll use a lot is to write plus R as an abbreviation for R equals true, or for just the abbreviation for true. The nice thing about writing plus R instead of true is that, 1, it's even shorter than true, and 2, you know what variable is true if you write plus R. If you just write true, that doesn't say anything about which variable. So that's often the notation we'll use for true, plus, and then in lowercase, the name of the variable. Minus R would be false for R. Temperature could be hot or cold. The time it takes to drive to work is a continuous variable, 0 through infinity. And the possible locations for the ghost in our case could be discrete coordinates. In this case, pairs of coordinates. We'll not deal a whole lot with continuous variables, but in general, they could be, in your domain, there could be continuous variables. Sorry. Your random variables could have continuous domains, but we'll not look at the math of those in this class. Okay, here are our running example random variables. Temperature could be hot or cold. Let's say they're equally likely. We'll represent that with a table with each entry being 0.5. So we have the values it can take on and then the probabilities associated with it. These probabilities mean that if you were to see this infinitely often, on average you see 50% of the time one outcome, 50% of the time the other outcome. For weather, we have 4 possible values in the domain: sun, rain, fog, and meteor shower, and corresponding probabilities. We put a 0 on meteor shower. We'll put a lot of zeros on the slides. If you build a real system, you probably don't want to put many zeros in there. The reason we put zeros on the slides is because then the math works out nicely. We can do math by hand. When you program something into a computer, there's no reason to make the math work out nicely. And you're probably better off putting something in there like 10 to the minus 10 or something, to at least capture that small probability that there could be a meteor shower. All right, so we have distributions. Distributions, essentially you can think of them as a table with 2 columns, the values in the domain and the probabilities. The probability for a particular entry is written this way. The probability for weather to be equal to rain is 0.1, this entry over here. Properties. Every entry has to be bigger than or equal to 0, and all entries have to sum to 1. Otherwise, it's not a probability distribution. Shorthand notation. On the right hand here, you have the long version, PT equals hot, PT equals cold, W equals rain, and so forth. If the values in the domains of your random variables are all distinct, you can abbreviate that and leave out the random variable you're talking about, because you know that hot only appears in the domain of the variable T. And so when you say P hot, you know that means probability of T being hot. The joint distribution can be over many variables, and often we'll have x1 through xn for kind of generality. Each variable will have a particular outcome. The joint outcome of all the variables will be one entry in our table. And we'll write, for one entry, we'll write it as follows: probability of x1 equals x1, and so forth, and shorthanded this way. So we have an example of a joint distribution here, 2 random variables, temperature and weather, and there are entries for all possible combinations of these 2 variables, and then associated probabilities. For the joint distributions with the same condition, every entry above or equal to 0, and the sum equals 1. What is the size of this table if we have n variables with domain sizes d? How many combinations do we end up with? About like the original state space sizes, right? If you're in a state space, you denote it with a vector. Each entry in a vector can take on d values. And there's n entries in your vector. End up with d to the n. So once we start working with lots of random variables, representing these tables is completely impractical, and we won't be doing that. But for now, we'll think of them as tables. Later, we'll see how to avoid having the tables explicitly. What's a probabilistic model? A probabilistic model is just something that you build by looking at the world, the part of the world that you care about, abstracting it, and then just making a joint distribution for it. It will be an approximation, as in any model we've built before, just now in the form of a joint distribution. Okay, we'll see a lot of ways of modeling very complicated domains in the next couple of lectures. For now, let's just assume you know how to do this. One analogy to keep in mind is the analogy with CSPs. If we just had CSPs and we wanted to reason about the domain, we'd have a table that might look like this, where we say what's possible is hot and sun and cold and rain, but these 2 are not possible. They're not very compatible. When back then I said we'll see a version of doing some kind of soft constraints, that's what we're seeing now. This, if we go up here, is a soft version of the constraints listed below. It's saying that 0.4, that's how good it is to have those 2, hot and sun. 0.3 here, but these 2 don't get a 0. Like the table below here would be similar to 0.5, 0.5, 0, 0. But here we can choose more fluidly what numbers we want to associate with everything. So we have a soft version of a CSP. What are events? An event is some outcome that you're interested in, and you want to then compute the probability for it. So it's a set, E, and there's some outcomes that are in that set. To compute the probability of an event, you just sum the probabilities of all the outcomes in that set. Okay? This can be very easily computed. It's just summing some entries in the table. Let's look at some examples. What's the probability that it's hot and sunny? Well, that means we have to look at the entries in this table that are compatible with hot and sunny, which is just this one over here, 0.4. Probability that it's hot. All compatible entries, hot is over here, these two entries, so 0.4 plus 0.1. Probability that it's hot or sunny. Hot over here, sunny over here and over here. Combine these three entries, and they sum to, let's see, 0.4 plus 0.1 plus 0.2, which is 0.7. All right, to make sure you're on the mark, let's start doing some quizzes here. First quiz about events. We have a table, we have 3 events, and I'll give you, for every one of them, 10 seconds. So in 30 seconds, let's check back in what your numbers are for these 3 event probabilities. All right, let's see what you got. How about the first one? Probability of plus x comma plus y. How much? 0.2 I hear. Plus x plus y, 0.2. How about probability of plus x? 0.5 I hear, which is 0.2 plus 0.3, correct? How about minus y or plus x? I hear 0.6, which is minus y here, here, plus x here and here. So together plus 6. All right, great. That's events. Marginal distributions. A marginal distribution is a distribution over a subset of the variables that you originally had. So you start with a joint distribution over many variables, and then you say, I'm only interested in a subset of variables. Give me the distribution over just that subset of variables. So here's a joint distribution over 2 variables. And we can turn that into 2 marginal distributions, one for t, one for w. How do we get the one for t? We look at the entries consistent with hot, sum them together, 0.5. That is these 2 entries here. Same for cold. It's these 2 entries here. Gives us the marginal distribution for t. That's marginalization, going from a joint to a marginal. We can do the same thing for w. We get 0.6 entries consistent with sun, 0.4 entries consistent with rain. Okay? The equation that we use for this is this one here. It's the kind of thing you want to start getting used to and looking at it and immediately understanding what's going on. What's going on here, we have on the right joint probabilities over 2 variables. We sum over one of them the values the variable x2 can take on. What that means is we keep x1 fixed because we're not summing over it. This means that we have an expression on the right-hand side where x1 is fixed. We sum over all possible values for x2. Jointly with that value of x1, that means we take all the rows in the table consistent with that value of x1. That is, we're computing the probability for x1. Okay, let's do a quick quiz again. Marginalization for this new table here. We have x and y. We should be able to read this off, so let's just have you call it out. How about this one here, plus x? 0.5, sum of these 2 entries, minus x, plus y, 0.6, and then minus y. All right, it's going great. Conditional probabilities. Usually what we're interested in is observing a variable and then based on that inferring something about another variable. That's where conditional probabilities come in. We have to define them first what they are. We have a distribution over two variables, A and B, and they have outcomes. And what we have here is we have two events actually. We have the event A. Oh, there's a typo. We'll call this here A. The probability for A lies in this region over here, B in this region over here, and the intersection is where both of them have their positive outcome. The probability of observing A as the outcome for variable A, given that we had B, is the probability of observing them together, because we need to observe them together to get A once we have B, divided by the probability of getting B originally. So what is that doing? It's looking at the region where B is and looking at what fraction of the time when we fall into this region do we also fall into this smaller region over here. Okay, so let's do an example. We have our joint distribution here, and let's look at the conditional for weather being sunny given temperature equals cold. All right, let's do the math. What do we have here? We have the joint over both of them divided by just the probability of what you condition on, t equals c. The joint has a probability of 0.2. It's this entry over here. The probability for t equals c, that's a marginalization. We have seen how to compute that. You take the entries consistent with that, which is this entry over here and this entry over here. So that's 0.5. We fill that in, and we get that the conditional distribution of sunny, given that we know the temperature is cold, is 0.4. Okay, let's do a couple of exercises here. Let's take a minute and a half for you to compute these and then round them up. All right, let's see what you got. Probability for plus x given plus y. Anybody? 1/3? That's what I'm hearing. How do we get that? It's the joint of plus x and plus y divided by the marginal for just plus y. And that is 0.2 over 0.4 plus 0.2. Which is 1/3. Nice. How about minus x given plus y? 2/3. We can just read that off from the previous one, right? They have to sum to 1, and the first one was 1/3, so the second one is going to be 2/3. Probability of minus y given plus x. I hear something 3/7. 3/5. Let's see. It's the probability of minus y comma plus x divided by probability for plus x. let's look at plus x. We have these two here, 0.2 plus 0.5. And for the minus y, we have the 0.3 here. And 0.3 up here, so 3/5. Great. That's nice. So we found all these solutions pretty well. Now, what we can do is if we know how to compute conditional distributions, let's say we have a joint distribution, we can compute a lot of conditional probabilities. So we had conditional probabilities here. We can compute a lot of these. We can combine them together in a table and give us something that we call a conditional distribution. In a conditional distribution, we fix at least one of the variables and let the other ones vary. So in this case, we only have two variables. We'll fix one of them. We'll fix temperature to be hot. And then we'll look at the distribution for weather. This is a conditional distribution. We could have just as well fixed temperature to be cold, and we'll get a different conditional distribution. These are two conditional distributions that we can find. There's two more by conditioning on weather to be sunny versus rainy. So there's a total of 4 conditional distributions that we can find from this one joint distribution. We picked the 2 where we condition on temperature. Together, we'll denote that as PW given T, both capitalized. So this notation here stands for 2 probability tables, 2 conditional distributions together. Think back to our sensory models for the measuring where the ghost is. You have a conditional distribution there. The sensory model will be of this type. What you have is something of the type probability of your sensor reading. Let's say the reading is R, given D, which is the distance of the ghost. And that family of conditional distributions here will consist of a set of tables, one for D equals 0, one for D equal 1, and so forth. All right. The normalization trick. We've computed conditional probabilities already. The normalization trick, something that in principle you could think you could do without, because it's just a quicker way of doing something you already know how to do, but we're going to do it so often that you really want to have this as a basic tool and kind of your mind as something you just do. You normalize, you don't think of it as a sequence of operations. So a normalization trick, what's happening? Let's look at conditional probabilities again. We can compute the conditional for sunny given cold. That's this expression over here. We can work that out based on entries in this table. All right, and then we can compute it. That's computing one conditional probability. We can now compute another one. For the other entry, now it's R instead of S. Same math. Here's what we have. Now let's carefully look at the computations we actually did. These are 2 separate computations. We could in principle do them separately. But what are the expressions that show up? Well, let's look at the denominator here and here. They have the same denominator. They're summing the same 2 entries together in the original table. Why? Because in both cases we're conditioning on T equals C. So we're dividing by the probability for T equals C, which is sum of certain entries in that table. And that's always what we have in the denominator. How about the numerator? Those are different entries. There's, in each case, one of the entries of the ones that you sum together in the denominator. This one here corresponds to this one here, and here is the right one. So another way to think of doing this computation is to say, if we have to compute a conditional distribution where we condition on T equals C, we could just look at the rows where we have C, which is over here. For sun, we take this, the 0.2. For rain, take the 0.3. Now we have the 2 numbers we need. And to find the denominator, we just sum those 2 numbers together and divide both by the sum of those 2 numbers. That's just a way of summarizing the computation we did. And that's the normalization trick. Let's spell this out a little more explicitly. You have your table. You select the joint probabilities that match the evidence. Our evidence in this case is T equals C. So we select those. Makes for a smaller table. This is not a distribution. Doesn't sum to 1. Just a subset of the entries in the original table. And then we say, well, we know that these are the only entries that matter. We just have to divide by the sum of them. So that's what we do. We compute the sum, divide by that, and we get the conditional that we were after. This doesn't just work with 2 entries. If instead of sun and rain, weather could also still be meteor shower and it could be foggy, you would do the same thing. You would now have 4 entries in your selection of the, in here. You would have another one for cold and meteor, another one for cold and fog. The probabilities wouldn't be these. Maybe it would be other numbers, but this always works. You just select the subset of rows consistent with the evidence, and then you take the sum of all the probabilities that are in that resulting table, divide by that sum, and that gives you the conditional condition on this evidence over here, which is how we pick the rows. That's the normalization trick. Why does this work? Well, we saw by example how this works. It's because when you compute the individual conditional probabilities, you always have the same denominator. And what is put in that denominator? Well, it's whatever you would have put in the numerator in each of the conditional probabilities summed together. Okay, so let's try it. Let's have you talk to your neighbors and find the distribution, conditional distribution for x given y equals minus y applying the normalization trick. Remember, that's a 2-phase process. All right, let's see how this went. First table here. This is going to be a table with still x and y and probabilities, but not a distribution anymore. It's only going to have the entries consistent with the evidence, which is minus y. So y will be minus y. We have that twice. One time with plus x, one time with minus x. The corresponding probabilities are 0.3, 0.1. To normalize, we need to compute the sum. Often that sum we call z. Z equals 0.3 plus 0.1, which is 0.4. Then we divide both of the entries by z, which is 0.4, to get x, y, b. And this is now the conditional for x given y equals minus y, plus x, minus x. We have 0.75 and 0.25. All right, that was normalization. What does it mean to normalize? Just to get the terminology straight, we saw the normalization trick, which is a way to go from a joint distribution to a conditional distribution by subselecting some rows and then normalizing. The last step is the normalizing. Normalizing, if you look at the dictionary, means bring to or restore to a normal condition. So normalizing, what that means depends on what's normal. We're going to make things normal. Normal condition in the context of probability distributions mean that the entries sum to 1. That's the normal condition. All right, so step 1 is compute z, which is the sum over all entries. Step 2 is divide every entry by z. Here was one example of the type we've just seen. We'll in the future see other examples that are very different. Here's another table. These entries are all bigger than 1. You can still normalize. Normalize just means sum all the entries together, divide by the sum to make them sum to 1. So here's what you get. Z is 50 in this case, and you get a normalized table on the right. Okay. Probabilistic inference for us and in AI means that you go from some distributions you already have available to a new distribution, often based on some evidence that came in. So typically we are interested in conditional distributions. For example, what's the probability of being on time given there are no reported accidents? Those the agent will then use as their beliefs to then use to maximize their expected utility. The interesting thing is that these probabilities can change with evidence that comes in. It could be that given no accidents and it's 5 a.m., the probability now is 0.95 that you're going to be on time, which is higher than when there's just no reported accidents. Then when it's in additional evidence that it's raining right now, probability of being on time goes down. And that's really what makes this whole process interesting, is that the more evidence you collect, typically the more accurate an estimate you get of what the probability of an outcome is going to be. And it can change, it could go up and down depending on the evidence you get to observe. In general, that renders ugly. Let's see. Go. All right. So in general, there's one procedure that will always work. It will continue to work over the next 4 weeks. It'll be expensive, so not our preferred procedure, but this always works. It's called inference by enumeration. What you do here is you start with a joint distribution, and then you just find the right entries in the joint distribution. What's the probability for sun? Well, probability for sun is probability of all the entries consistent with sun. So that's this one, this one, this one, this one. Sum all 4 of those together is 0.3 plus 0.1 plus 0.1 plus 0.15. Anytime somebody asks you for probability of some outcome of a set of variables, you can just look at the consistent entries in the table. Here's a conditional query. Well, we know how to define that in terms of ones that look like this. That's the probability of sun, comma, winter, divided by the probability for winter. And then we can do the same thing again. We can just look at all entries consistent with sun and winter, which is here and here. So 0.1 plus 0.15 divided by all entries consistent with winter, which is these 4 entries, which happen to sum to 0.5. Here's another one, sun given winter and hot. Again, we can put this in terms of just probabilities over variables rather than conditionals. Sun and winter and hot divided by probability of winter and hot. Look up the consistent entries for the numerator, sun, winter, hot. It's this one here, 0.1. Winter hot is these 2 entries, which is 0.1 plus 0.05. You can always do this. No matter what query you get, you can run inference by enumeration. This is how you do it. This is an example, but this is in general the algorithm you can apply. A lot of symbols here, so let's step through them. These will keep coming back in the next few weeks. There are evidence variables. So, in general case, we're interested in a query of the type probability for Q given E1 through EK. The variables that are observed are called the evidence variables. The variables you're interested in, and this could be a set of variables, doesn't just have to be one, is the query variables, or query variable Q. And then there are other variables, because your joint distribution might have many, many more variables in it than the ones that are observed and the ones that you're interested in. Those are the hidden variables. We'll never get to observe those. We're not interested in those, but they're there. You might ask, why are they there? Well, sometimes it's easier to build a model with lots of variables than to compact the model right away to the variables you care about. So then you have a big model, and then when the query comes in, only some subset of variables will be relevant to your query. Okay, so that's our query. How do we do the inference by enumeration? You look at the full table, you knock out the entries that match the evidence. Then you sum out the hidden variables to get joint of query and evidence. What does that mean? The entries here, you will look at every possible value the query variable can take on. And the evidence variables are fixed. For every value the query variable can take on, there will be a row in the table that comes out of here, out of the squeezing operation. And the entry in that row, the probability listed there, is the sum of all the probabilities of entries consistent with the evidence and with that instantiation of the query variable. After you've done that, you normalize and you have the answer to your query. To do this mechanically on the example we had here, let's do one of these mechanically according to the inference by enumeration mechanical procedure. Let's do this one. Sun given winter. What's the mechanical procedure? Pick everything consistent with winter, take it out of that table and retain it. That's this part here. That's what we're left with. Then for every possible value the query variable can take on, our query variable here is sun. That really belongs to the random variable W. So really we're after the distribution for W given winter. So we're trying to find PW given winter. We can take on sun or rain. So we'll have an entry for sun and for rain. The evidence variables are already fixed. Then we have to sum the consistent entries we have for sun 0.1 and 0.15. Sum together is 0.25. For rain we have these two, also 0.25. Now we normalize, z is 0.5. And as the resulting table we get for the table for W given winter, a table that looks like this. W, E, W given winter, 0.5, 0.5 for sun and rain. That's the mechanical procedure. Very straightforward to program. You can do it for any joint distribution, any conditional query, and you can get the right result this way. What's the worst case time complexity? And why do we have all the future lectures in some sense is that, well, worst case, you have to look at pretty much the entire table, which is ordered d to the n. So that's bad. You have to store that much. You have to store the joint distribution. So it might not be very efficient once we have hundreds of random variables. But for now, it's a mechanical procedure that in principle, if we're willing to wait long enough, could make work. Any questions about inference by enumeration? Okay, I'm gonna exceptionally skip the break just because I forgot the mic in the beginning and we're gonna run out of time otherwise. So let's go on to the last part of lecture. Sometimes what you get is not the joint distribution, you get something else. And you can then often build the joint distribution from that, and then you can run inference by enumeration, answer the original query. That's the most typical case. So here's an example. You are given the conditional of x given y, which could be a sensor model, some prior of where y might be, what values it might take on. And I'm going to claim that that's equal. If we multiply them together, we get the joint for x and y. Why is that? The conditional for x given y is defined as the joint over the marginal for y. Just moving y over here, or equivalently multiplying both sides by p of y, we get the expression on the left. So anybody gives you just this and this, that's equivalent to giving you the joint distribution. You can build all the entries in the joint from having the marginal for y and the conditional for x given y. Let's look at an example. We have weather and dry or wet. We have a marginal for weather, a conditional for dry or wet given weather. To build the joint, we have to apply product rule, which is shown over here. How does that work? Well, we have an entry for every possible combination. This entry here would be probability of sun times probability of wet given sun. We look that up. Sun 0.8, wet given sun 0.1. So we find the product 0.08 and so forth. Okay, that's the first way of constructing distributions. We'll see a lot of more advanced ways of constructing distributions in the next lecture, but this will be the building block for that. Now, you can start doing this with more random variables. The joint distribution for x1, x2, x3 can be written as the marginal for x1, conditional for x2 given x1, and then the conditional for x3 given x1 and x2. More generally, you can write the joint over n variables, x1 through xn, as the product of conditional distributions of each variable xi given the variables that precede xi. This sign over here means product over all factors of this type for I, if you want to make it more explicit, for I equal 1 through n. So if you had, for example, product I equal 1 to 3 xi, that would be the same as x1 times x2 times x3. A lot like the summation notation, but now for products. Why is this always true? Why is it guaranteed that for any joint distribution you can rewrite it in this format over here? And not only in that format, you can do it in n factorial different ways, because for any ordering of your variables, you can do this. So we have now, with this expression, have n factorial alternative ways of writing our joint distribution. Let's see why this is always true. We have, let's do it by example here. What is this expression here? Let's start with this one here, actually. Px1, let's just keep that. Then Px2 given x1. That's the joint over x2 and x1 divided by the marginal for x1. And the next one here, that's the joint for x3, x2, x1 divided by joint for x2 and x1. The pattern you see here is that you get these cancellations, and you're only left with the last one. And this will always work. If there were another variable x4, we could have x4 given x1, x2, x3. And then we here would have x4, x3, x2, x1 divided by the joint over x3, x2, x1. And now these two would cancel. So this always works out. And it doesn't matter whether you order the variables x1, x2, x3 or x2, x3, x1 and so forth. You just pick an ordering and then stick with it. This is the foundation of how Bayes nets work. And that Bayes nets will be our main representation going forward. But this is the foundation that is always valid. All right, Bayes rule. Bayes rule is a way to kind of get a distribution in some format, slice it up, and spit it back out in a different format. The starting point is that when you factor a joint distribution, as we just looked at, you can do it in two ways. The joint is the marginal for y times the conditional of x given y, or you can switch the roles of x and y. There's nothing particular about each of these roles, and you just as well have the marginal for x times the conditional of y given x. Now let's say we divide both sides by px. Then we end up with actually let's divide by py. Px given y then becomes equal to py given x, px over py. That's Bayes' rule. That's saying that if somebody started by giving you a conditional for y given x and some other information, you can turn it into a conditional for x given y. All these problems that we had as motivation in the beginning of the lecture, we said it's easy to build a model one way, and then what you really want is to invert that model to find the answer to your inference query. Well, that's what Bayes' rule will do for us. It will typically be easy to build a model one way. Let's say it's easy to build this model for y given x, and then when you get your evidence, and assuming you have these marginals, you can turn that into a conditional for x given y. Okay? That's the same thing over here. That's the Reverend Bayes. And he owns that rule. If you had been around back in his days, that little computation there could have made you own a rule. And you should really think of it that way. You should think, like, if this rule doesn't look so simple to you that you don't understand why somebody got their name for it, you got to keep looking at it and keep studying it. You got to know it that well and look at it and say, this is so trivial. How come somebody has their name associated with it? That's when you're in good shape. Okay, why is this helpful? Well, it's the whole reason of that sometimes it's easy to find things in one direction and then you can run inference with Bayes' rule and find the other direction. So let's look at a typical example. Even though we make fun of it, it's actually one of the most used equations in AI, so it's really important, and that's just what it's called. The typical inference problem that we will look at with Bayes' rule is one where you say it's easy to build a model for the distribution over effects when you know the cause. Because you might say, we know this is true. Let's say you had a superpower, you knew where the ghost was, then you could go around with your sensor and see as a function of where the ghost is, you could measure the probability of each of the outcomes of your sensor. And that's the model, that's how you calibrate your sensor. Whenever you have a sensor, this thing over here is really the calibration of your sensor. The reverse model is much harder to build. You can't calibrate your sensor and come up with this model here. Why? Well, you see it in this equation here. This is physics. This is how your sensor works, how it is noisy, and how there's cause and effect. But then these here are pieces of prior information. How often a certain cause might be present. What's a typical occurrence? How often does a certain disease occur? How often does a ghost sit next to a wall or something like that, right? Those causes, the things you're interested in, you often have a prior distribution for them, and you might not know that ahead of time, and it's definitely not a part of your sensor calibration process. Your sensor is just about, if the cause is fixed, this is what the sensor will do. Okay, so here's an example. We're interested in diagnosing somebody. Let's say we're given this model here. What's this saying? The probability of having a stiff neck, given that you have meningitis, is 80%. Probability of having meningitis is 0.0001, so pretty low. And the probability of having a stiff neck is 0.1. What we're interested in is the probability that somebody has meningitis after they told us they have a stiff neck. Okay, well, we don't have that given. That's the cause given effect that we're interested in. So we apply Bayes' rule. We fill in the numbers, and we get the posterior is 0.0008 for meningitis given they have a stiff neck. Why is it still low, even though this number is so high? Well, it gets multiplied with this number over here, which is the prior for meningitis, which happens to be very low. One thing you might wonder now, well, what do we do with these probabilities? Just as a note, it's not because the probability is low that you might not act upon that, right? If you have an expectancy max 3, and there's a probability sitting in there, even if it's low, if the utility related with that particular outcome is very high, it will still have an influence on the expected value. And so in this case, you might still want to go to a doctor and get things checked out. Why? Because the utility value of not getting it checked out and having meningitis is extremely low, right? you pass away. That's the lowest, for most people, the lowest you can get. It's just something to keep in mind. So I'm going to let you do this quiz on your own and revisit Ghostbusters so we can get till the end here. Let's say we have two distributions, the prior distribution over ghost location, and a priori we have a uniform distribution shown over here. There is a sensor reading model, and we saw the table for that a while back. What then happens is, whenever you get a measurement, you apply Bayes' rule and find the posterior distribution. One interesting thing about the application of Bayes' rule is that you often get away with this thing over here. What is that thing? What we really should be computing is P ghost given R equal R given ghost, probability ghost, divided by probability for R. And we'll do this for all values of G. What does that mean? When we do that for all values of G, that means for all values of G, the denominator will be the same. And what is this denominator here? PR. PR is equal to sum over G, the joint for G and R, which is the same as the sum over G of the probability for G multiplied by the probability of R given G. That's this expression over here. So what we see is that in the application of Bayes' rule, if we're interested in a posterior distribution, the full posterior distribution, all entries for where each location of the ghost, computing one of them, this part is specific to that one, but this part here, the denominator is shared and happens to be equal to the sum of the numerators of all of them. And so often what you do is you use the normalization trick. You say, oh, I can compute the table before normalization by leaving this out. And then we put this thing over here instead of an equal sign. That's the unnormalized posterior distribution. And then all we need to do after that is sum all entries and divide by the sum over all entries to get the posterior. Independence. So, two variables are independent in a joint distribution if the following holds true. You look at all entries in the table, and you have to verify this condition. Is it true that the entry for x and y is equal to the product of the marginals for x and y taking on those values? So you have a 2 by 2 table, so a 4-entry table with two random variables with 2 entries each. You have to check 4 equalities. If all 4 of these are true, then you would have independence. So keep this in mind. This is for all x and y. We write this as x independent of y. Now, what that means is that your original distribution can be written as a product of simpler distributions that are one-dimensional distributions rather than two-dimensional distributions. That's nice because that often simplifies the representation. Typically, it's a modeling assumption. Very few random variables are really independent. Now, if you think of, for example, weather, traffic, and cavity, could you think of any of these being independent of each other? Well, maybe you could. You could say cavity is independent of weather and traffic. Because whether I have a cavity is not really that related to whether there's a lot of traffic and how the weather is. You could say, well, maybe they are related because when I have a cavity, everybody has a cavity, everybody's driving to the dentist, and so there is a strong relationship. You never know, right? But in a reasonable model, you would say cavity is independent of weather and traffic, unless you really want to capture something about people visiting dentists all at the same time. This is similar to a notion we had in CSPs where we had separate graphs for independent subproblems. That's what independence is here. Distributions that have independent variables corresponds to having independent problems. What's an example of where that really happens? Actually, we're running out of time. Let's just start with this next time, the example for independence, and stop here for today.